and thanks a lot for joining to this talk on differential regression testing for REST APIs. I'm Daniel Lehmann and I'm going to present joint work with Patrice Godefroy and Marina Polishuk, both from Microsoft Research, and myself at University of Stuttgart. Before I come to our approach, I first want to motivate why it is important to look at REST APIs. So REST APIs are typically used to provide programmatic access to web services. So that could be for mobile application or automation, but most importantly, they are used in cloud services such as Microsoft Azure or AWS. In a typical REST API interaction, a client and a server communicate via HTTP. So say the client sends a GET request and the server responds with a structured list of posts, so for example JSON data, and then the client decides to modify a certain resource, here with the HTTP put verb. REST APIs have been tremendously successful as a simple model for interacting with cloud services, and as such, services and APIs have been evolving very quickly. So here on the lower right corner you see an Azure API, and over the course of 3 years the number of unique endpoints in this API has increased a lot. And during this evolution and this growth, it is very important to ensure that there are no regressions for existing clients. And in the past, regressions in cloud services have caused very severe outages, so it's important to prevent them. One option to prevent breaking changes is a staged rollout, for example. So you first make the API available to early adopter customers and only then roll it out at a certain region and only finally make it available to all users of a public cloud. But this has still the problem that it catches bugs only after they have been introduced in production. This can cost in the meantime a lot of developer time and potentially also money if you break service level agreements. So a better option is to do testing before deployment, but manual testing is often laborious and many developers find it quite boring. So a more interesting approach is to do automated testing, for example implemented by RESTler. And the idea here is that you generate some random inputs, so for example a random request, you send it to the program under test, to the service, and then on the output you decide whether this constitutes a bug or correct behavior. So for example, a 500 internal server error is almost never correct, so most certainly this is a bug. But the problem is that for some outputs, the decision is not so clear. So for a 200 OK, for example, you might not be sure, is the resource actually existing? So shouldn't it have been a 404 not found instead? One way to solve this oracle problem is to employ differential testing. And the idea here is quite simple. You still generate random inputs, but you give it to 2 instead of 1 programs. And then you observe or compare the behavior of the 2 programs against each other. And if one of them behaves differently, then it might have a bug. And this, of course, only works if the programs are related in some form. So, for example, this has been very successfully applied to compiler testing, where the 2 programs are different implementations. So one could be GCC and one could be Clang. Differential testing can also be used to find regressions in programs. And here the idea is that you don't test 2 different implementations against each other, but 2 different versions of the same program. So you generate inputs for the old version of the program, and then you give it to both the old and the new version. And the assumption is that the new program, if it's backwards compatible, should behave the same on those old or previous inputs. And if not, then you have potentially found a regression in the new version. We want to apply this idea of differential regression testing to REST APIs, but before we do that, I first want to highlight a crucial difference between regular programs and REST APIs. And that is that in a regular program you have a single component that is being updated, namely the program itself. But in REST APIs we have multiple software components. So the first one is the service itself, of course. But a second one is a specification of the service or the REST API. So for example, here you see a Swagger or Open API specification of an Azure REST API. And then once the specification is published, third-party developers can develop clients against this specification or derive clients, sometimes even automatically. And we as a service owner or an API owner want to make sure that there are no regressions in those artifacts under our control, namely the specification and the service itself. Given those 2 software components in a REST API, we observe that there's also 2 different types of regressions in REST APIs. And the first type of regression is a regression in the service itself. So that could be that previously accepted request is now no longer accepted. So for example, the response changes from 200 OK in the old version to 400 bad request in the new version, which is certainly a breaking change for clients. And another regression in a service is, for example, if the response of the service now contains a new unexpected property, and this might cause clients, for example, to be unable to pass this property and then crash. The second type of regression in a REST API are regressions in the specification. So the idea here is that the service itself is correct, but the new specification makes it difficult for third-party developers to derive or implement new clients for this specification. So an example of that could be that your old specification had a request specified, but the new specification either removed or renamed that particular endpoint. And then this makes it impossible for new clients to provide implementations for this request. Or another example of such a regression is that a request in the new specification suddenly requires a property that was previously not required. And this again can break clients or can break implementers of clients because they are unable to produce values for this required property. Now, to find those two types of regressions, we want to instantiate the differential regression testing idea for REST APIs. And what you see here are, again, the two components, the service and the specification, both of the old version N. And then the first update step happens, namely of the service components. So that means a new service is now online, and this new service is able to handle, for example, new requests or supply new features. And then we can do differential testing between the responses of the two different service versions on the same requests coming from the old specification. And then if there's a difference in the responses, we can potentially find a regression in the new service version. And then the second update step is when the new specification is published by the API owner. And this new specification can then be used by third-party developers to develop new clients that make use of the additional features, for example, in the new service version. And now differential testing compares the responses from the same service, namely the new version, but on requests from the old specification versus requests from the new specification. Now, finally, to make this process automated, we cannot really wait for third-party developers to write those clients against a new specification version. But what we can do is we can use the automated testing approach as implemented in RESTler, for example. And that exactly takes in a specification of a REST API and then generates requests matching that specification. And then we can direct those requests either to the old service version or the new service version. And with that, this process here is automated, and we can only use as input a specification of a certain version and a service of a certain version. Now, in this figure, we only talked about two REST API versions, namely version N and N+1. And for each such version, there was a specification and a service. But in practice, we can have N API versions, and for each such version, we have a specification and a service. And this gives us a roughly n² number of combinations to test, namely in this upper triangular matrix, we can always have requests generated from an old specification targeting at least this service version or a newer service version, and not the other way around, because you can't test new requests on older services. But this is not yet differential testing, right? So one cell in this matrix is one combination of specification and service, and this is one observed behavior. But what we wanted to do is we wanted to compare two different behaviors or service outputs against each other under two different combinations. And this means what we have to do is we have to compare two cells in this matrix. And the comparison in this direction are service updates where the specification stays constant. And the other direction is where the service, the targeted service, stays constant, but we compare the behavior on old requests or requests from the old specification versus requests from the new specification. And this means in total we have to test each adjacent combination of adjacent cells in this matrix, and this again gives us roughly n² number of diffs. So the process is twofold. First, we do the automated testing for each combination of specification and service version, and then we do a comparison against between each adjacent cell in this configuration matrix. Now, as to how we compare two test configurations against each other, I don't want to go into too much detail here for time reasons, but the high-level gist is that the result of a test configuration run is a network log, and that is essentially a sequence of request and response sequences. And then we recursively compare two such network logs with each other after abstracting away some unnecessary details, for example, non-deterministic HTTP headers like date or etag, or properties in requests that are only coming from resources that were allocated by the fuzzer, for example. A second aspect of our diffing is that we have two variants of it. One we call the stateful and the other one the stateless diffing. And we employ stateless diffing whenever we compare network logs of two different specification versions against each other, with the reason that a new specification version sometimes reorders requests or introduces new requests, which we don't want to appear as regressions. But when we compare network logs from the same specification version, we can use a more precise stateful diffing that, for example, takes the order of requests into account. For more details on the diffing and the network logs, please have a look at the paper. All right, so finally, we want to know whether our approach on differential regression testing for REST APIs actually works in practice. And for that, we did an evaluation on historical versions of Azure APIs. To be precise, we looked into Azure DNS and networking services. So they can be used, for example, to create firewalls or load balancers or to configure IP addresses. And the cool thing is that all their specifications are publicly available on GitHub, as you can see here on the right. And then for each API, we looked into 17 historical versions, going back until 2016 and up to 2019. And in total, all the APIs and all versions of the APIs was quite a large API surface. So the specifications of these APIs was more than 4,300 files and more than 600,000 lines of Swagger specifications and examples. For collecting the network logs of each potential test configuration, we had to evaluate 159 combinations of specifications and service versions, which took about 3 days and 8 hours. Following the data collection, we then looked into the diffs between two testing configurations. And in those diffs, we found 14 regressions in total in 5 different APIs and services. And we saw also that there were both types of regressions in our findings. So we had some regressions in specifications, for example, where a previously specified endpoint was renamed and no longer available to third-party implementers of the specification. And we also found service regressions where the service, for example, returns properties that are not specified and thus could break clients when they try to pass this response. What was also encouraging to see is that we found that both diffing directions are necessary to find the regressions. So we found 5 regressions when comparing across 2 different specification versions, but keeping the service constant. And we found 9 regressions where we used the same specification to generate requests, but targeting different service versions. In total, we had to inspect about 272 diffs, so combinations of different test configurations, and that took about a week of manual effort. To give you a better impression of the regressions that we found, I also want to show some examples. And the first example that I have here is an example of a specification regression. So on the left, you see an old version of a specification, on the right, a new specification version. And when we generate requests from those 2 specifications and send them to the same service version, once it returns 200 OK, and on the new version, it returns 400 bad requests. So clearly that is a regression, and you can see the reason is that some properties have been incorrectly moved. And a version later, the specification gets fixed, which is good because it confirms that this was actually a bug. And now the interesting point is that 2 months later, the specification is regressed again, and somebody entirely removes this location property. And then a bit later, again, there is a fix and the original state is recovered. So what we see from this is that such errors occur, and it is very necessary to have tooling to find such regressions before deployment. The second example I want to show is, again, a specification regression. And what we see here is that some endpoints from an API were entirely removed, going from February to April 2019. And what we see is that somebody else also found this change, and actually it was a breaking change for them. So again, good that we can find this kind of regression. And finally, the third example is one where the service has regressed. So we sent the same request from the same specification to two different service versions, once February 2018 and once service version April. And what we see is that the response is almost entirely the same, except that in April it returns a new property. And this property is not actually specified and could thus potentially break clients parsing this response. And with that, I would like to conclude my talk by giving a short summary. So first, I introduced differential regression testing for REST APIs, which is interesting because there's two different software components, a service and a specification. And consequently, there's also two different types of updates and also potential regressions, namely when publishing a new service and later when updating the specification and making that available such that third-party developers can derive or implement clients against the specification. And in our approach, we take different of those testing configurations, so where requests generated from one specification are sent to service versions of the same or a later version. And then we compare two such test configurations against each other with a certain diffing approach. I didn't go into too much detail about this diffing of network logs. For more details, please have a look at the paper. And finally, I also talked a bit about our results. We found 14 regressions in real-world Azure APIs. And I also gave some examples how those regressions look like and what our approach can help to find those regressions. And with that, I'd like to say thank you for your attention, and I'm happy to take questions in the video session at ISSTA 2020. Goodbye.